Hello! Happy Friday. Today, I think, is a good day to talk about geometric sequences and geometric series. Remember the difference. A sequence is a string of numbers, like 3, 9, 27, 81, 243. A series, instead of a sequence, a series is adding up a whole bunch of numbers. So 3 plus 9 plus 27 plus 81. So we're going to do both today. We're going to talk about geometric sequences, which we've seen a bit before, and geometric series. How do we add these up? Okay, so we're starting out with 3, 9, 27, 81. These look familiar? What are we doing each time to get from one number to the next? Think to yourself for about 4 seconds. How do we get from 3 to 9 to 27? Just think to yourself. Alright, now turn to the person next to you. What are we doing each time? Alright. Ben, what do you think? Exactly. Multiplying by 3 each time. Okay, so what is this? This is 3 to the n, right? We're starting off with 3, and then the nth term is just 3 to the n. We say that it is geometric because there is a constant ratio. Let me write that down real quick. Constant ratio between the terms, namely r equals 3. So far, so good. Nothing too complicated. It would be nice if we could get a more general sort of approach to these. These obviously have something to do with exponential functions. So we're going to get a formula that looks kind of familiar, because it's pretty similar to what we did back in October or so with exponents and logs. We're not doing logs here, but it'll look kind of familiar. So we have a sequence. Ours is 3, 9, 27, 81, but it could be any geometric sequence with the constant ratio. You start out with some number, a1. To get to the next one, you multiply by whatever your ratio is, r. To get to the next one, you're going to multiply by r again. So it's like you took a1, multiplied by r again. You multiplied by r squared to get the third term. To get the fourth term, we have a1 times r cubed. Yeah? Because whatever you started with, multiplied by r once, twice, 3 times to get the fifth term, you have r to the fourth. In general, when you're looking at the nth term, it's whatever you started with times n minus 1 copies of r to the n minus 1. So for this example, we have 3 is our first term times 3 to the n minus 1, which, if we remember our exponent properties, 3 to the 1 times 3 to the n minus 1 is just 3 to the n. Yeah, and that's what we got before. So we're good. So our general formula, if we have a geometric series that starts with a1, has this constant ratio of r, is going to look something like, what's it going to look like? A sub n equals a sub 1, r to the n minus 1. Right, that's what we just derived. Where r is the constant ratio. Constant ratio between the terms in a1 is the first term of the geometric series. Okay, so let's look at one example, and then I'll turn you guys loose to work on a few by yourselves. You see that okay? These are all on Brightspace, so if you don't have it yet, go ahead and look on Brightspace. So we're starting out with 10, 20, 40, 80, 160. Okay, is this geometric? Are we multiplying by a constant ratio each time? To get from 10 to 20, we multiply by 2, times 2 gets you to 40, times 2 gets you to 80. Yeah. R is 2. This is indeed a geometric sequence. It's hard to get the angle right on this. Okay, so what's our formula? It's not just 2 to the n, it's not 10 to the n. Okay, so we'll go back to our formula, right? We said we have to do a1 times r to the n minus 1. Right, that's our formula for a sub n. We know what a1 is, right? Our first term is just 10. We know what the constant ratio is. R is just 2. So it should look something like that. Actually, I think we can clean this up, make it look just a bit nicer. Because 10 is the same thing as 5 times 2. So I can do that. Why would I do that? Well, like before, what's 2 times 2 to the n minus 1? That's 5 times 2 to the n. Does this work? Let's see. If I plug in 1, 2 to the first is 2. 5 times 2 is 10. That's our first term. If I plug in 2, 2 squared is 4 times 5 gives me 20. If I plug in 3, 2 cubed is 8 times 5 gives me 40. Yeah, this seems to work pretty well. So this formula right here, pretty good formula for geometric sequence. I think at this point you can handle examples 3, 4, and 5. So please take a few minutes. Look at examples 3, 4, and 5. Take about 10 minutes for those, and then we'll come back together, go through them, and then we'll talk about geometric series. How do you add all these up? Take a few minutes, do examples 3, 4, 5. I'll see you in a few.